Good afternoon. Good afternoon, ladies and gentlemen. And now it's our turn to give you our presentation about physical properties of water, which is our Group 4 project. And within this project, we divided up into 4 different chapters. First, electrical conductivity, which is about how much and how well can some of the solutions conduct electricity. And the second part is density, and about how water density changes with temperature. And third part is the intermolecular force, because between all particles in this universe there are certain forces, and we are just investigate what is the specific intermolecular force within water. And the fourth is the polarity of water, which is very important. And about these 4 chapters, I'm going to explain the electrical conductivity and polarity. And my partner Tony, he will explain the density and the intermolecular force. And first, electrical conductivity. Our aim was to compare and explain the difference in electrical conductivity between water and several kinds of drinks. And these drinks are bought from the schools market, which are very familiar to us. And this is how the parachute was set up, and also with the JLX Explorer. And the method is first is to set up the parachute as shown in the picture you have just seen. And second, we add 15 milliliters of water to the beaker, and after 1 minute, record the reading from the sensor. The sensor is very artificial intelligence, and it is able to give out all the data. And third, we just repeat the above steps with different kinds of drinks. And these are the data we got for the water, orange drinks, red tea, green tea, and no food tea. We actually need more than these, but we just put 5 up here. And there's another special kind of solution, which is the MyZone. The components in it are very unstable, and the electrical conductivity is changing all the time. And for this part, our conclusion is water has the lowest electrical conductivity rate compared to other drinks. And second, water has a very low amount of positive ions moving in uniform direction. And the second conclusion is the result of the first one. Because within water, all the hydroxide ions and the hydrogen ions are bounded together by the hydrogen boundary. But in some other drinks, we have other components like some metal ions in it. And the free ions moving would be able for the solution to conduct electricity. And that's the density. Tony will explain it to you.
Hi everybody. As we all know, most matter in the universe, they expand when they're heated, and then they contract when they're cooled. However, through research on the internet, our group has found that water behaves differently in a range between 0 and 4 degrees Celsius. And so, for this experiment, we decided to use calculator-based laboratory technology to observe the anomalous behavior of water between 0 and 4 degrees. And here is how we set up our experiment, and Mary will show you first later on. The method was, first we set up the apparatus as shown, as Mary is doing right now. The cylinder was filled with 500 ml of liquid, which was being tested. And then the temperature at the top and the bottom of the liquid were recorded differently for 6 minutes using a JLX Explorer. So basically, from the picture here we can see that there are 2 strings each attached to the top and bottom of the liquid. And so we were able to measure the temperature changes at the top and the bottom of the liquid respectively. And that's how our apparatus is shown and set up. And so from the Explorer, we gathered these results. For oil and alcohol, we found that the temperature at the top of the sensor remained constantly above the temperature at the bottom of the sensor. And the reason why this is because the liquid at the top of the water is closer to the surroundings and will absorb heat more easily than at the bottom. And so it is heated quicker. However, for water, we can see that it behaves differently. Somewhere throughout the experiment, the temperature crossed over between the top and the bottom. And the reason why this is because water contracts when it is heated and expands when it is cooled between 0 and 4 degrees Celsius. So when temperature increases a certain amount during the experiment, the water at the top becomes denser than the water at the bottom. So then they convect and the water at the top moves down to the bottom and vice versa. And so that's why we have a crossover in our graph. And next is the interspatial extension between polar and non-polar molecules. As anyone who studies chemistry knows, antimolecular force acts differently between polar and non-polar molecules, varying in their strength. Polar or dipole-dipole forces tend to be stronger than non-polar bonding. And so, to investigate this on a more clear scale and to make it easier for other people to see, we decided to add drops of liquid and allowed them to spread out on a flat piece of glass and was shown onto a wall for magnification. And the shape and the spread of the different liquids were compared. Now, here's the pictures we got. As you can see, this part here on the right, that's water. That's just water drops. And because water is a polar molecule, the intramolecular forces are stronger. And so the water tends to be bound more tightly than the thing on the left. And this is alcohol. Alcohol is a non-polar molecule. And so intramolecular forces are much weaker than that of water. And so the alcohol drop spreads out more than the water drop. And here's different pictures from different perspectives. And now we'll talk about the polarity of water.
The first unit is the polarity of water, in which is the polarity of water makes its molecules charged because the electronegativity of hydrogen and oxygen are different. And non-polar molecules are not charged as the total dipole moment of the molecules is 0. And for this experiment, we did it with first, as you can see on the picture, there's a rubber stick. We first scrap it with a piece of leather and make it charged, and then the liquid in here is water. And we can see that the charged rubber stick attracted the water line, and it is now it's a curve instead of a straight line. And this picture is not very well shown yet, because in here we have used trifluoromethane, which is also the weak polar molecule. The last one is the tetrafluoromethane, which is non-polar, and we can see from the picture that it is not affected and the liquid just drops in a straight line. And this is the introduction of our team members.